And now the brilliant, that was already one brilliant move, but here comes another brilliant move. I have to erase this. Let's take these two quantities and subtract them. So what I want you to do is this. I want you to do, what is S sub n minus r times S sub n? So tell me what happens here. If I ask you to take this and subtract this, what happens? Lots of things cancel, don't they? Right? So this AR gets subtracted, right? So these two are going to go away when I subtract. These two are going to go away when I subtract. These two are going to go away when I subtract, right? This A didn't have anything to subtract, so it's still there. Now come down here, what happens here? This one right here, does it cancel? What's the one right before this one? Isn't the one right before this A r to the n minus 1? Isn't it just one less power than this? So this one is here, isn't it? They cancel. How about this one? It's not up here, is it? So this one stays, doesn't it? So what we have left when we take this row and subtract this row is the A out there, right, on the top left, minus this one. Got it? So I have A minus A r to the n. What I'm trying, I keep on saying what I'm trying to do. What we are trying to do is get a nice formula for S sub n. If we could get a nice compact little formula for this, instead of this big old sum, then maybe we have a chance. So up here on that equation, notice these both have S sub n. Let's factor an S sub n out. If I do that, what's left? 1 minus r. Right? Because you have to distribute that back through. Solve for S sub n. Divide both sides by 1 minus r. And what is great about that formula right there? I have a formula, right? If I ask you to let n go to infinity now, nothing is going to start racing away from me. It's not like I'm adding things up anymore. Do you see that? So I'm not going to have this tail end just start going off. It's just, all it's going to do is just change what the power of that number is. So the only piece of this problem that has any impact by n, or is the only piece that's impacted by n, is that r to the n, right? So now, if I take the limit as n goes to infinity of S sub n, I get limit as n goes to infinity of a minus a r to the n over 1 minus r. Anybody recognize the part that's in red here? I'll give you a hint. About 48 hours ago, 47 hours ago, you were looking at this with me. We had limit n goes to infinity of r to the n. And we were looking at this and saying, what does this do? And we came up with the conclusion that it could do one of a couple of things. It should be in your notes. It depends on r, doesn't it? If the absolute value of r was less than 1. Do you remember me writing that down? Is that in your notes? Okay. If the number down here, if the base is smaller than 1, what does this go to? The limit of that. So here's an example. 1/2 is less than 1, right? Raise it to the n power. Let n go to infinity. What happens? Goes to 0. This thing goes to 0, doesn't it? Now, do not confuse. I'm not saying this sum goes to 0. Just stick with me right here for a minute. Now, what's the other cases we had? if r was 1, this thing goes to 1. And if the magnitude was greater than 1, it did what? It went to infinity, or diverged. That's from last class, right? So let's come back over here and let's talk about what this limit does. And guess what it's going to depend on? It's going to depend on r, right? So this limit can be one of a couple of things. Let's first talk about what happens, the easy case, when the absolute value of r is less than 1. So what happens when the absolute value of r is less than 1? This piece goes to 0. So if this goes to 0, then all you're left with is, that's all gone. You're left with what? No, the a's gone too, because this is 0, right? That's going to 0. So that's all gone. Just a on top. And on the bottom, 1 minus r. That's what the infinite sum will converge to if the magnitude of r, if the absolute value of r is less than 1. Now, let's skip r equals 1 for a minute, okay, because that's actually the most confusing case. What if the magnitude of r is bigger than 1? Well, then this piece right here is going to go to infinity, right? And if this piece goes to infinity, all these other numbers are constants. That means this whole thing becomes infinite, and it diverges. So, well, it'll be negative infinity on top, but this is going to be a negative number also, because r is bigger than 1. So 1 minus the number that's bigger than 1, that's going to be negative, and negative over negative is positive. So it'll diverge. The whole point is it diverges. All right? Diverges. Got it? Didn't I tell you that a geometric series is either going to converge or diverge? It's going to converge if the absolute value of r is less than 1. It's going to diverge if the absolute value of r is bigger than 1. There's only one thing left that we have to consider. What if r equals 1? Well, the problem with that is we cannot plug 1 in here for r, can we? Because we get division by 0. So you sit there and you go, well, that's a big problem. You know, like, we can't do it. The formula breaks down. But to take care of the case that r is 1, just go back to the formula for a geometric series. Didn't I say it was ar plus ar squared plus ar cubed plus dot, dot, dot? What if r is 1? If r is 1, then isn't this a plus 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 a plus, right? Forever. Do you think that converges or diverges? Doesn't matter what number you give me, right? If I take the number, let's say, 1/10 plus a 10th plus a 10th plus a 10th, and keep on stacking them on top of each other forever, that's going to become infinite, isn't it? So it's going to diverge. If r is 1, it's going to diverge. So you see the difference? The sequence, r to the n, converges if r is 1, but the geometric series diverges. So I should probably just put a line under this inequality, because that would mean if the absolute value is 1, then we're going to diverge. And that's it. That's the main result. Okay? So let me kind of sum it up. So in summary, for a geometric series, a plus ar squared plus dot, dot, dot forever. This is equal to sum n equals 1 to infinity of a to a sub n, which equals, ar to the n minus 1, which equals sum n equals 0 to infinity of a r to the n. So those are the two different notations we have for geometric series. This will converges to a over 1 minus r if the absolute value of r is less than 1, and it will diverge if the absolute value of r is greater than or equal to 1. That is the main thing. The geometric series is one of the few series that we can actually find what it converges to. That's what I was telling you. On the test, if I say find the sum, it's because you actually have a formula for the sum. So let's do an example. Let's do the problem that I put up here as your first example of a geometric series. Let's find the sum. 3 plus 3/10 plus 3/100 plus 3/1000 plus ... forever. Let's find out what this adds up to be. We first have to verify that it's geometric. You have to do that first. You have to prove to yourself that this is geometric. So this is where you come in here and go, okay, this is 3 times 1/10 to the 0 plus 3 times 1/10 to the first plus 3 times 1/10 squared plus ... And then turn that into the sigma notation. Sum n equals, I'll use 1 to infinity of what? 3 1/10 to the n minus 1. And just double check right now that this formula works. Double check it. N is 1. 1 minus 1 is 0. 1/10 to the 0 is 1. 1 times 3 is 3. I get that one, right? Let n be 2. 2 minus 1 is 1. So I get this one. 3 and... Yeah, we're good? We're happy? And that looks exactly like the formula. I'm going to put the formula here because we're going to reference it again. I'll put it up here. Okay. That's our grandmaster formula for geometric series. So all I need to do is determine what r is, right? If the magnitude of r is less than 1, then I'm just going to plug that formula in, plug my a in, plug my r in, and I'll be done. So from this, I notice that a is 3, r is 1/10, and of course, the magnitude of r is less than 1. So it converges, right? Therefore, it converges to a over 1 minus r. R was 1/10. Let's clean this up. This is 3 over 1 minus 1/10. That's 9/10, isn't it? This is the same as 3 over 1 times 10 over 9. So division is the same as multiplication of the reciprocal. And this gives you 30 over 9. And we can reduce 10 thirds. 10 thirds. That's the correct answer. That's the way you leave it, 10 thirds. Now, just for our own sake, isn't 10 thirds 3.3333 repeated forever? Yes. Isn't it? Can we convince ourselves that that's true? This is 3, right? 3 plus, what's 3/10 as a decimal? 0.3 plus, that's 3/100ths. That's 0.03 plus 3,000, 0.003, right? Forever? Isn't that just 3.33333? Yeah? Okay. All right, I'm going to change it up a little bit. I want you to find the sum, and let's do 5. No, let's go 7. Let's use a different number. 7 over 1,000 plus 7 over 10,000 plus 7 over 100,000. See, make sure I get all my zeros right because I messed up my class earlier today. I left a 0 off, even though I said it right. I left a 0 off. Okay. You get the idea? So when you look at that, you have to be thinking geometric. Does it look like each of the denominators have something in common? Do they look like they're all powers of 10 again? Something, right? The 7s are always the same? So you might be thinking right now A is 7. That's wrong. So that's why you need to pay attention to what I'm about to do. This is 7 times, okay, I can get 1,000 by doing 1/10 what? Cubed. I can get 10,000 by doing 1/10 to the 4th. I can get 100,000 by doing 1/10 to the 5th, and so on and so forth, right? So you agree with me that that's it? Now, turn this into sigma notation. Sum n equals 1 to infinity, 7, then what? 1/10 to the n plus 2. Why does it have to be n plus 2? Because it starts at cubed, doesn't it? N plus 2. If I let n be 1, this is going to be a 3. That'll give me my first one. And then 4, and then 5. Does this look like this? It has to be n minus 1 in the formula. This has to be an n minus 1 for the formula to work. It's not an n minus 1. So what I'm going to do is I'm going to force there to be an n minus 1. And this is where I'm going to use that idea of a hidden 0. We've used this in the past. So I'm going to rewrite this as sum n equals 1 to infinity, 7 times 1/10 to the, I want n minus 1, right? I'm going to go n, here it comes, minus 1 plus 1. That's my hidden 0. What was already there, though? Plus 2. I know that looks like, what in the world are you doing that for, right? Like, that's crazy. It's like, take one step forward, take one step back. But it actually saves us, because look at this. So look at this. If you split it along there, you have two pieces, right? You have the n minus 1 piece, and then you have 1 plus 2, which is 3. And if I separate it, right, if you have the same base, right, if you have x to the n times x to the m, you add the exponents, right? Same, that's here. X to the n over x times x to the m. You add these. If I add those back together, I'll be back here and I'll be back here, right? So this is the same. I mean, like, you could actually go straight from here to here if you wanted to. And that has a big impact, right? Because now I have something to the n minus 1, and this piece is really just a number, isn't it? This is 1 over 1,000. And I can just paste that onto the 7 in front. And so I have equals sum n equals 1 to infinity, 7 over 1,000 times 1/10 to the n minus 1. See how I did that little clever algebra here? 1,000, 1 over 1,000 is this. Bring it out front with the 7. And now, is that geometric? Does that fit into that formula up in the top left? Yes.
So is your A 7 over?
Yeah, so what's A? This is geometric. Our A is 7 over 1,000. And what's our R? 1/10 again. And of course, the absolute value of R is less than 1. So this converges.